Hi, welcome back to another Math 111 video lecture. I'm going to give you my screen here and we are going to talk about section 5.3. All right. So what I want to talk about with you today, let me fix that. There we go. Is section 5.3, which is all about the zeros of a polynomial function. Now, the zeros mean where y equals 0, or where the function equals 0, because those really are the same thing. Or, what's the other word for this? The x-intercepts. So what we're talking about here really are the places where the function, the polynomial function, interacts with the x-axis. It'll either touch or cross the x-axis at the zeros. So what this means, if we've got a polynomial function, like 2x to the third minus 3x squared plus 5x minus 7. Your textbook talks about something called the remainder theorem. And it turns out that if I think about taking some polynomial function and I divide that by x minus a number, okay? And I get some new function plus some remainder. It turns out that that remainder is the same thing that I would have gotten if I had plugged this number r into my function. So, for example, suppose I want to find for this function over here p of 5. I'm going to show you a couple of ways to do that. One way is we could use our calculator. And I'm going to show you how to use your calculator to do this fairly quickly. What we're going to do is we're going to actually put this function into our calculator. So push the y equals button. Clear out anything you might have in there. And just type in 2x to the third power minus 3x squared plus 5x minus 7. Okay. Now, we're going to do something you might not have ever done before. So I want you to pay attention to the buttons I'm pushing. And I'm going to use a different tool so you can actually see what I'm going to do. Okay, so what I'm going to do is I'm going to actually go look at a table of values. So push the second key and then the graph key. Now, you'll notice my table of values is pretty empty. Yours might not be. I will show you how to get it to look like this. So go into Table Setup. That's TBLSET. That's the blue letters above the window key. So push the second and then the window. And you'll get a screen that looks like this. Now yours probably actually looks like that. What I want you to do is use these arrow keys right over here and move your cursor down to where the first, that IND, PNT, that stands for independent. Think X when you think independent. Change that to ask. So arrow down and then arrow over and then hit enter to make the selection. Now go back into your table by pushing the second key and the graph key. And your table is going to be empty. Just type in the x value that you want to evaluate the function at, and we get 193. That's one way of finding the functional value. If we had found a 0, that value would be 0, because that's what the zeros are. The other way of finding a functional value is to take advantage of this remainder theorem and just do synthetic division. So P of 5 is the same thing as the remainder of 2x to the third minus 3x squared plus 5x minus 7 over x minus whatever number we care about. In this case, care about 5. Okay? So I'm going to do synthetic division with 5, the number that I want to evaluate the function at. Drop down the 2. 5 times 2 is 10. Add. Multiply. 5 times 7 is 35. Add those two together. 5 times 40 is 200. 200 plus negative 7 is 193, which is the value I got when I plugged 5 into the function. Okay? You may be thinking to yourself, what's this got to do with the zeros? Well, what it has to do with the zeros is that if a number, a, is a 0 of some polynomial, then the remainder of that function, that p of x, divided by x minus that number, will be 0. So the remainder is 0. The function's not 0, the division is not 0, but the remainder will be 0. And if I plug a into that function, I will get 0. And, yes, there's more. The binomial x minus a is a factor of that polynomial function. Okay, we can use that last little bit to play some games. So let's suppose that we're asked to find a polynomial such that p of 2 equals 0 and p of 1 equals 0. And p of negative 2 equals 0. Now, let's look at what I just told you a minute ago. What I said just a minute ago was that if some number a is a 0 of the polynomial, then, and this is the part I want you to key on, x minus that number is a factor. So we're told that 2 is a 0. We're told that 1 is a 0. And negative 2 is a 0. That's what this statement means. If p of 2 equals 0, that means that 2 is a 0. If p of 1 equals 0, that means that 1 is a 0. And if p of negative 2 equals 0, then negative 2 is a 0. So we can build a polynomial where these three numbers are all zeros because If 2 is a 0, that means that x minus 2 is a factor. And if 1 is a 0, that means that x minus 1 is a factor. And if negative 2 is a 0, that means that x minus a negative 2 is a factor of our polynomial. We can take these three facts together and build our polynomial by multiplying our factors together. Now I'm going to write this one as x plus 2. Okay, now we can simplify this guy fairly simply, and I'm actually going to reorder my multiplication. I'm going to start by multiplying x minus 2 times x plus 2, because I know that that's x squared minus 4, and we'll keep the x minus 1. Now multiply through x squared times x is x to the third power. Negative 1 times x squared is minus x squared. Negative 4 times x is minus 4x. And negative 4 times negative 1 is plus 4. And this polynomial has got zeros at negative 2, negative 1, and 2. You can check me by plugging them in or by graphing it. All right, so let's try another example. This is some kind of cool stuff. So now let's answer the question, is x minus 4 a factor of the polynomial 4x to the third minus 16x squared minus 9x plus 36. Okay, now I'm looking at this one, and it will factor. So I could actually factor this polynomial, and I can see that there's a pretty good chance that x minus 4 is going to be a factor. But let's suppose that you're not very practiced at factoring, and you don't want to try to factor this thing. But you remember that your math teacher told you that if x minus 4 is a factor, then the remainder of the quotient of the polynomial divided by that factor will be 0. So what we're checking to see is, if I do this division, is the remainder 0? Well, let's check. You can use log division, but I'm going to use synthetic division. So I'm going to do synthetic division with the number that is subtracted by 4, or sorry, subtracted from x, which in this case is 4. And then I put my coefficients alongside my box. Drop down my first coefficient, multiply 4 times 4, and I get 16. And add, I get 0. Multiply 4 times 0, and I get 0. Add those two together. 4 times negative 9 is negative 36. And my remainder is 0. So the answer is yes. X minus 4 is a factor. And furthermore, we know the other part of the factor. We know that my original polynomial can be written in factored form as my factor, which is x minus 4, times the result of the division, which is 4x squared plus 0x minus 9, or 4x squared minus 9. Now, this isn't fully factored, but that's beyond what we want to do. Our question at this point was just, Is it a factor? All right. So why do we care? Well, we care because if x minus 4 is a factor, so x minus 4 is a factor, that means then that 4 is a 0. We are building up our skills to be able to solve polynomial equations. And let's just try one of these. So let's do this. Let's say I posed a slightly different question. And what I told you to do was solve the equation 4x to the third minus 16x squared minus 9x plus 36 equals 0 if x equals 4 is one solution. Now think back to Math 95 or whatever the last algebra class you had was. And think back to what you did with quadratic equations in order to solve them. You factored them, right? You factored them because then you could set each factor equal to 0. And that's what we're going to do here. So what we know, and this, by the way, is the same polynomial we were just working with. What we know is that if x equals 4 is a solution to this equation, that means it's a 0 because my equation equals 0. Is a 0. Then x minus 4 is a factor, which we already proved. So what we can do is divide that out and write our polynomial in factored form. So we divided out our factor, and now, so we're going to divide. And rewrite our polynomial in factored form. So my equation now becomes, so I started with 4x to the third minus 16x squared minus 9x plus 36 equals 0. But I divided out my x minus 4. Remember, I did that right over here. So when I divided out my 4x to the third minus 16x squared minus 9x plus 36, I divided that by x minus 4. I got 4x squared minus 9, which means that this here, this piece, my 4x to the third minus 16x squared minus 9x plus 36, can be written as x minus 4 times 4x squared minus 9, and that still equals 0. Now we need to completely factor. So we have to look at this second factor here and remember that it's a difference of perfect squares. And remember how it factors. And it's going to factor as the square root of the first term, which is 2x, minus the square root of the second term, which is 3, times the same thing, plus. This comes from a squared minus b squared equals a plus b times a minus b. That's the factored form for a difference of perfect squares. Okay, now I've got 3 factors, all of which, if I multiply them together, equals 0. Think back and remember something called the zero factor property. The zero factor property says that if I've got 3 factors all multiplied together to equal 0, at least one of those factors must equal 0. So that means that x minus 4 has to equal 0, or 2x minus 3 has to equal 0, or 2x plus 3 has to equal 0. In other words, the only way to get 0 out of a multiplication, is to be multiplying by 0. Okay? So if I solve each of these 3 linear equations now, that means x equals 4, or solve this one, add 3, and then divide by 2, x equals 3 halves, or solve this one, subtract 3 and then divide by 2, so x equals negative 3 halves. So my solutions to the equation 4x to the third minus 16x squared minus 9x plus 36 equals 0, the solutions to that equation are x equals 4, x equals 3 halves, and x equals negative 3 halves. That also means that if we were to graph that polynomial equation, that function would either cross or touch the x-axis at each of those values for x. And later in this chapter, we will talk more about that graphing of polynomial functions. Okay, I think that's enough for today. I think I even won't give you a quiz on this one. I know that I gave you a lot to process and a lot to think about. Try in your own head, to make sense of the connection between zeros, factors, and the remainder, and solutions to equations. All right, I will see you all again soon. Have a great day.